Hello everyone. In today's discussion, we discuss a very interesting question from the functional analysis part, and this question is asked in the TIFR-CAM PhD Mathematics exam 2026. In this question, what is given here? F is a mapping from the real number set to the real number set, and it is a continuous function. Along with this, it is given that f of 0 is equal to 1 and f of x is equal to 0 whenever modulus of x is strictly greater than 1. Okay, and the sequence of function fn x is defined in this way, means fn x is equal to f of x plus n, means fn is the simply the translation of f by n for every small n belongs to the natural number set and x belongs to the real number set. Then we have to verify these three things, means whether fn converges in the L infinity R and whether fn converges in the LPR for some p1 to infinity, and and third option is saying that fn converges in LPR for all 1 less than equal to p less than infinite. Okay, before going to discuss these things, first of all I will assume that you all are well acquainted with these spaces: L infinity space, LP space. These are all Banach spaces, means these are all complete normal space, and these spaces are associated with some norm. With respect to that norm, these spaces are complete. Okay, all are Banach spaces. I hope that you all are well acquainted with these spaces here. Okay, so in the question given, f is a continuous function and f of 0 is equal to 0 and f of x vanishes whenever the modulus value of x is strictly greater than 1, and the example of such type of function is look like this. Okay, it is an example of such type of function. Okay, and fn x are the nothing but the translation of this function, means f of x plus 1 will like translate like these things. Okay, these are the translation of things, and fn x is defined in this way, and this is the translation of f by n. Okay, so where small n belongs to the natural number. Now we will evaluate the pointwise limit of this sequence of function. Okay, so we take any arbitrary point x0 belongs to the domain R. Since x0 is a finite real number, then we can find a natural number n0 belongs to the natural number set capital N, such that this relation will hold for every small n greater than equal to n0. Simply one can take a small n is greater than 1 by x0 if one can take, or if one can consider this as your n0, small n0, these things plus 1, then it will gives this thing. One can consider these things, or one can simply take n0 is equal to 1 minus x0. Okay, 1 minus x0, then it will satisfy these things for every small n strictly greater than n0. Okay, this implies what? The limit value of these things is equal to 0, because it is vanishing at the point x0 for every n greater than n0, and when n goes to infinity, so it gives equal to 0. But our x0 point is the arbitrary real number, so this implies that the pointwise limit of this fn is equal to 0 for every x belongs to the real number set. So we infer a very interesting property that this sequence fn has pointwise limit which is equal to 0. Okay, now we will move to verify the option 1. Option 1 is saying what? Option 1 is saying that whether this sequence fn converges in L infinity. This sequence fn converges in L infinity arrow. We have to check that whether it is a true statement or false. Okay, before going to verify these things, first we have to establish this nice property. It is saying that L infinity norm of Fn is equal to L infinity norm of f for every n greater than equal to 1, and in addition it is saying that the L infinity norm of f is greater than equal to 1. So we have to verify this. Since we know that Fn is nothing but the translation of f. Translation of f means if you draw the graph, these things, then f1 will look like the same, but it will shift to right hand side because it will be translated by 1. So it shift, this same graph will shift to not right hand side, maybe in the left hand side. The graph will shift either left hand side or the right hand side. Okay, but since our natural number n is a positive thing, therefore it will shift to the left hand side, but whether it may shift right or left, there is no problem, but the supremum value will remain same because the graph will remain same. Okay, so it is from the geometry it is clear. One can also verify these things mathematically, that supremum norm of L infinity norm, here not the here notation is wrong, L infinity norm of these things is same equal to this thing. Okay, one can also mathematically prove it. It is your homework, you should prove it mathematically. Okay, now it is given that now we have to check that the L infinity norm of these things is greater than equal to 1 also. Okay, we are given that f is a continuous function, it is given. Okay, and continuous function has a nice property that continuous function on R. Okay, on R it is given. So it has a nice property that the L infinity norm means the essential supremum of f is equal to the supremum of f. It is a nice property. Means here in the left hand side L infinity norm is there. Here we have to calculate these things in the sense of essential supremum. I hope that you all know about what is the meaning of essential supremum. Essential supremum means you have to calculate the supremum value by excluding a set whose measure is 0. But in the supremum case, you have to calculate at all the points. You cannot exclude anything. But in the essential supremum case, you are allowed to exclude a set whose measure is 0. Okay, I hope that you all know these things. But for the continuous function case, essential supremum is equal to the supremum. It is a nice property. But in addition, we have given that f of 0 value is equal to 1. So since f of 0 is equal to 1, then this supremum value, supremum of x belongs to our f of x, is always greater than equal to 1. Since at one point it is 1, therefore supremum value is greater than equal to 1. So it implies that the L infinity norm of f is also greater than equal to 1. And here I am not providing the proof of that this essential supremum is equal with supremum for the case of continuous function. I will provide this proof link in the description box. Okay, means it is a stock exchange link proof, and I will provide it in the description box. Okay, you can check it. So we establish this nice property. This one is true. So now we will prove that option 1 is false. Okay, option 1 is false. We will prove it by using the method of contradiction. So we take that option 1 is true. Okay, suppose option 1 is true, then we will reach to a contradiction. That contradiction verifies that our option 1 is false. Okay, so suppose that option 1 is true. Option 1 is true means what? Our sequence Fn converges to some function f in the L infinity R space. Okay, this implies this thing Fn minus f L infinity norm converges to 0 when n goes to infinity, and its equivalent definition is this thing because it is in the L infinity norm, means essential supremum norm sense. So therefore we can find a subset of R whose measure is 0, such that this convergence is in the sense of uniform convergence. But here the supremum is taken over R difference P. It is the equivalent definition of the L infinity norm. L infinity norm says that we can find a set P whose measure is 0, so that on the set P complement Fn converges to F uniformly. So it is coming. Okay, since Fn is converging to F uniformly on the set R difference P, and we know that uniform convergence implies the pointwise convergence. So therefore Fn converges to F where? Therefore Fn converges to F on this R difference P in the pointwise sense, because uniform convergence implies pointwise convergence, but uniform convergence is on this set, therefore pointwise convergence is also on this set. Okay, but this set P has measure 0, so one can directly say that one can directly say that Fn converges to F almost everywhere. Okay, here Fn is convergent to F almost everywhere. But in our previous equation 1 means here we have already shown that Fn converges to the 0 function at every point. So here means in equation 6, therefore this fx value is equal to 0, and this value is 0 on this set, and since the P set has a measure 0, therefore our F is almost everywhere 0, and we know that in the LP function or L infinity functions, these functions are treated in the sense of almost everywhere sense, but we have established that F is almost everywhere 0, means F is a 0 function. So in the equation 5, in equation 5 means where here you can put in place of F you can put F is equal to 0, because we have established that F is almost everywhere 0. So by putting that 0 functions here in equation 5, you will reach to this conclusion, and this conclusion implies what? The limit n tends to infinity, the supremum L infinity norm of Fn converges equal to 0. Okay, so we get this equation 8. But from equation 2, if you look at the equation 2, equation 2 is here. If you look at the equation 2, the L infinity norm of the Fn function is always greater than equal to 1, this thing. And if you take the limit on the both sides, this limiting value is also greater than equal to 1, this thing. Okay, and these two things are contradicting. It is a contradiction to it, because it is saying that the limiting value of this Fn norm of L infinity norm of Fn is greater than equal to 1, but it is saying that the limit value of the Fn L infinity norm of Fn is equal to 0. So these two things are contradicting each other, and this contradiction is coming due to the assumption that Fn converges to F in L infinity. So this assumption is wrong, means the equation 1 is false, this option 1 is false. Okay, this is false option. Now we will verify the option 2 and option 3, and option 2 and option 3 will be verified at a time, means we will prove that Fn does not converges to F for any P. If we can prove this thing, then both options will be false, because it is saying it will converge for some P and it is converges for all P. But we will show that Fn does not converges in LPR for any P. Okay, so therefore these two options will also be false. Okay, let us move to prove this. Okay, we will verify. Means our claim is that Fn does not converges in LPR for any P belongs to 1 to infinity. How can you prove it? Let us proceed. Okay, so it is also proved in the same way by the contradiction argument. We will take that Fn converges to some function f in LP space for some P. For suppose for some p it is converging, but then it will give contradiction. Then it will imply what? It does not converge for any p. Okay. This implies what? Fn is converges in LP means we can find a function LP function in this space, which is a Banach space, so that this limit is equal to 0. Let us call this equation star. Okay. And the LP norm is defined in this way. It will be used. Next we will claim that LP norm of Fn is equal to LP norm of F, because Fn are nothing but the translation of F. One can also mathematically prove in this way by using the change of variable formula. It is a simple calculation, you can follow it. Then our next target is prove that the LP norm of F is greater than equal to these things for some delta greater than equal to strictly greater than 0. We can find a delta strictly greater than 0 which satisfies this relation. And if we want to establish this relation, since our Fn functions are also equal with this LP norm of F, then all these Fn functions will be greater than equal to this quantity, positive quantity. Okay. So let us proceed to prove this property B. Given that our function f is a continuous function, okay, and f of 0 is equal to 1. Since f is continuous on the whole domain, in the particular case at x equal to 0, it is also continuous. Now we will apply the definition of continuity at the point x equal to 0 by taking epsilon is equal to half. Then we can find a delta greater than 0 so that this relation is true for every x belongs to in this interval, open interval. Okay. And after simplification, you will reach to this step that f of x value is greater than strictly greater than half and strictly less than 3 by 2 for all x in this interval minus delta to delta. Now we will proceed to calculate this LP norm of f power p. Okay, then we will get this thing. It is coming from the definition of the LP norm of f. And this is, since the integrand is a non-negative quantity, if you shrink the domain, then here greater than equal to sign is coming, because this value will be lesser than this. Okay. Next, on this interval minus delta to delta, its minimum value is half. If you put this half, this sign will be preserved, greater than equal to, since this value is greater than equal to this value. Okay, because we are putting the lowest value here. Lowest value is half. Okay, in equation 9. Okay. So after simplification, you will get that 2 delta, because it is a constant quantity, it comes out integration value gives 2 delta, and 2 delta divided by 2 to the power p. So if you take the 1 by p power on both sides, you will get this thing. So we established that from a and b, from a it is coming this, and from b it is coming. Therefore we established this equation relation 10. Okay. And this relation will be used to prove that Fn will not converges to F for any p. Okay. Before going to prove, we will use a very interesting result in the functional analysis or measure theory. It says that for 1 less than equal to p strictly less than infinite, if Fn converges to F in the LP space, then we can find a subsequence of Fn, which is Fnk, such that Fnk converges to F pointwise almost everywhere. Okay. But if you remember in the previous part that we have shown that the pointwise limit of Fn is 0. Okay, for every point. But it is saying that these Fnks are the nothing but the elements from the Fn. So that pointwise limit we have already established in equation 1. If you can go in the previous part, we have established that in this our pointwise limit value is 0. Okay. So we can use that thing here. So this pointwise limit is always equal to 0, because it is true for Fn, and Fnks are nothing but the elements from the Fn, because Fnk is a subsequence. Therefore these are also elements from this. So this fn case also satisfy this pointwise limit is 0. So therefore f is a 0 function. Therefore our limit function f is a nothing but a 0 function almost everywhere. But LP functions are treated in almost everywhere sense. So we can treat f is a 0 function. Okay. So if you put f is 0 function in equation star here, it is the star equation. If you put here 0, it gives what? Limit n tends to infinity, fn norm LP norm is equal to 0. So it gives this thing here. Here means here. If you put the value f is equal to 0 here, then you will reach to this thing. Okay. But we have established in equation 10 here that fn LP norm of fn function is greater than equal to this positive quantity. So we have already established. Therefore this will also true for the fnk, because the fnk's are nothing but the elements from the fn sequence, because it is a subsequence. So if you take the limit, then this limit will be greater than equal to this positive quantity, and it is just strictly greater than 0. But in equation 11 it is saying that it is equal to 0. So these two things are contradicting each other, and we are getting contradiction because we are assuming that fn converges to f for some in the LP space for some p. Therefore we are getting contradiction. Therefore it implies what? fn does not converge to converge in the LPR for any p. So for any p it is not true. Okay, means for all p fn does not converge. Okay, means if you take any p, then you are getting that fn does not converge. So it is saying that for some p it will converge it. So option 2 is false, and option 3 is saying that fn converges in LP for all p. So it is also false, because fn does not converges in LPR for any p. So therefore these all three options are false. This implies what? Option A is saying that all are true, so it is false. Option B is saying that 1, 2 true, it is false. Option C is saying that 1 and 3 true, it is a false. Option D is saying that all are false, so it is a right option. Therefore only option D is true. I hope that you all understood it very well. Thank you all. Bye bye.